Hello everyone! In this video we will continue to examine topic 7.3, the structure of matter, and in particular we will finish up discussing the history of the models of the atom. So in 1913 it was discovered that, or sort of in this time period really, there were a whole bunch of discoveries that happened around this time. But it was discovered that the planetary and nuclear model, even according to the best physics of the time, would fail. It's a very, very deep mystery because accelerating, orbiting electrons of the type that were important for this planetary/nuclear model should very, very quickly radiate away their energy and spiral into the nucleus. This very quickly, we're talking a fraction of a second that this should happen. Fundamentally, this has to do with sort of electricity and magnetism, and you can sort of visualize it a little bit by thinking about what would happen to the field lines of a positive charge if you were to, say, take that positive charge and move it around or wiggle it. Imagine you were just to move it in this direction. What would happen, or move it in a circle? What would happen to those field lines? Well, what would happen is that the field lines don't instantly change given where it is. So what would happen is the field line sort of close by to the particle would appear to sort of wave outwards, and you would get propagating waves out from that central particle as it spun around in a circle. And what a wave in the electric field is an electromagnetic wave. These electromagnetic waves would take energy with them. And so what would happen in theory is that the energy of that orbital rotation of this electron here would very, very quickly be lost in the form of radiating electromagnetic waves. Now, straightforwardly, this does not happen. And that central mystery was responsible for Niels Bohr introducing what was known as the Bohr model at the time. And this is the precursor to our modern day understanding of the atom. This is the first quantum model of the atom. And we've already sort of discussed its foundations. So this is the model of the atom where electrons can only occupy quantized energy levels, and the electron transitioning between those energy levels is responsible for photons of particular energies either being absorbed or emitted in the form of atomic spectra. So incredibly strong evidence for this Bohr model of the atom came from the fact that the atomic spectra, as discussed in topic 7.1, could be very, very accurately predicted using this general idea. Now, at higher level, there is a tremendous amount more to learn about sort of these steps, and I don't want to get bogged down in the details, but suffice it to say that due to wave-particle duality, this idea that electrons and other forms of matter exhibit properties of both particles and waves, that you can interpret the electron as sort of a standing wave around the central nucleus. Why are only certain energy levels allowed? Well, they're only allowed because you need to have an integer number of wavelengths for the wave that corresponds to the electron, known as the wave function, around the central nucleus. So each one of these energy levels is secretly something that looks a little bit more like this, where you have integer numbers of wavelengths allowed as the electron itself forms a standing wave around the proton. And this is due to a phenomenon we know as wave-particle duality, but in some ways that is just naming something quite mysterious, which is that electrons and, for that matter, photons exhibit properties of both particles and waves. HL will delve into this in much, much, much more detail. So that takes us to this quantum model of the atom where we have quantized energy levels and quantized other things as well. And we interpret that electron not as sort of a tiny little ball in orbit, but as some kind of standing wave. Wave in what? Well, that is a fair question, and I am going to save it for the HL material and another day. And then finally, if we take that model, sort of that two-dimensional wave structure, those two-dimensional standing waves as the Bohr model, we can then say, well, that doesn't quite work when you do the math out for larger atoms, and did not really capture what a three-dimensional electron wave would behave as, even though it had tremendous success in allowing us to predict the results of atomic spectra mathematically. It did not, in fact, capture what most atoms even were like. In part because most atoms are not sort of these two-dimensional structures. This is clearly just a model for what is going on. And the equations governing how to get the same sort of standing wave for a three-dimensional model are much, much more complex, but led us to what is now known as the modern Schrodinger model of the atom, where orbitals, which is a term often seen in chemistry, are what corresponds to the electron, where in truth what the electron is this sort of probability density cloud. It's worth noting that this cloud is simply a visual representation of the solutions to the wave function, this kind of thing, in three-dimensional space. HL, as I said, is going to learn a lot more about sort of how we get from the fundamental physics to these particular shapes known as orbitals. But suffice it to say that it involves quite a bit of math and is fundamentally just due to the fact that atoms can get more complicated than just hydrogen, and you need to be able to deal with the fact that this probability density cloud is in 3 dimensions.